Hello students, welcome to my YouTube channel Integrated Physics Studies IPS. एथरे मु ऑलरेडी प्लस 2 सेकंड ईयर सिलेबस कंप्लीट कर सारछि एबे मु प्लस 3 सीबीसीएस ऑनलाइन क्लासेस रो वीडियोज गुडा अपलोड करिवि जदि भल लागिला ताले लाइक कर देबो एवं सब्सक्राइब कर देबो जो वीडियोज गुडा मु अपलोड करिवि तार नोटिफिकेशन पई एठी बेल आइकन को ऑल रे सेट कर देबो गोटे इंपोर्टेंट जिंस वीडियोज रो ऊपर एठी जो 3 डॉट्स देखुछो तार क्वालिटी एठी देखो बाय डिफॉल्ट 360 अछि तमे ताकू पढे मध्ये परिबो एठी एडवांस रे क्लिक करी तमे रिजोल्यूशन बढ़े परिबो प्रति वीडियोज रे मु पीडीएफ लिंक देबी ताकू एठी ड्रॉप डाउन लिस्ट रो तमे क्लिक करी डाउनलोड मध्ये करि परिबो पीडीएफ को लास्ट रे एठी जो मोर चैनल नेम अछि याकू क्लिक करी तमे एठी प्ले लिस्ट को जाई मु प्रति वीडियोज को यूनिट वाइज एज पर सिलेबस सजाई की रखिथिबी तमे सर्च करि परिबो ओके थैंक यू
हेलो स्टूडेंट्स आज टॉपिक रे हमें एप्लिकेशन ऑफ स्क्रॉडिंजर इक्वेशन टू द केस ऑफ पोटेंशियल स्टेप ए विषय रे पढ़िबा ऑलरेडी तमे पोटेंशियल स्टेप विषय रे क्वांटम मेकानिक्स रे पढ़ी सारछो एंड दिस इज वेरी मच सिमिलर टू दैट वन so for this we have to consider the potential energy function which is varying with respect to x such that this Vx is equal to 0 for region 1 where x is less than 0, right? And this Vx is equal to V0 for the region 2 having x greater than 0, right? Let us have now some qualitative discussion. So for this, if we consider the incident particle, okay, having suppose energy E, now it is incident from left, okay. Now obviously this is a barrier, okay, you can see in the figure the particle which is incident from the left, this will be acting like a barrier, this boundary, okay. Now according to classical mechanics, if this energy E is greater than V0, okay, this barrier is having a height V0 at position x is equal to 0. So if the energy of the particle is greater than V0, then classically the particle is able to penetrate this barrier and continue to move in the positive x direction, right? But however, the kinetic energy of the particle in the region 2 will be lower than that of your region 1. On the other hand, if energy is less than the barrier height, that is V0, then the particle will be reflected back at x equal to 0 due to insufficient kinetic energy, so that it will not overcome this barrier, right? So this is what the classical point of view. But quantum mechanically, actually what happened, for the case of E greater than V0, there will be a chance of particle undergoing reflection at the barrier, that is at x equal to 0. So classically we saw that for this case the particle will be completely penetrating this barrier, but quantum mechanically some part will be transmitted and some part will be reflected. This we will discuss in detail onwards. Now for the second case, that is for E less than V0, although the reflection coefficient, which is the ratio of reflected current and incident current, so this reflection coefficient capital R will be equal to unity, okay, this we will derive. Now for the wave function, what will happen, this wave function actually will be non-zero, right, in the region x greater than 0, that is in the right side, right? So as per quantum mechanics, even in case of energy less than the barrier height, that is V0, still then there is a finite probability of finding the particle in the region that is x greater than 0, that is in the region 2, okay. This we will also discuss onwards. So first let us have some mathematical analysis. So for this we will apply the Schrodinger equation, which is d square psi x by dx square plus 2me by h cross square psi x equal to 0. This is for region 1, that is x less than 0. Similarly for region 2 we have the same format, only there is a difference of minus v0, which is the barrier height for the region 2, that is x greater than 0. Okay, now equation 2 and 3 we can write this as by replacing this 2me by h cross square to be k1 square. Similarly, 2me minus v0 by h cross square, let us replace it by k2 square. Okay, so this will be a simple replacement of Schrodinger equation, okay, with k1 and k2. Then the general equation of equation 4 and 5 will be psi 1x equal to a exponential I k1x plus b exponential minus I k1x. Similarly, for the region 2, we have psi 2x equal to c exponential I k2x plus d exponential minus I k2x. Okay, and here psi 1 and psi 2 are the wave function for region 1 and 2 respectively, and a, b, c, d are your arbitrary constants, which we will determine by using the boundary conditions. Okay, now if we multiply the wave functions psi 1 and psi 2 by a factor exponential of minus iet by h cross, then the terms a exponential ik1x and c exponential ik2x will represent the waves which are propagating along the positive x direction in the region 1 and 2 respectively. Similarly, the terms b exponential minus I k1x and d exponential minus I k2x will represent the waves which are propagating in the region 1 and 2 along the negative x direction. Remember, this power, if positive, okay, if positive this power, then it is propagating in the positive x direction, and if this power is negative, then the wave is propagating in the negative x direction. Now, since the particle strikes the barrier at x equal to 0 and it is coming from left, right, so there cannot be a wave which is propagating in the negative x direction in region 2. Okay, hence we must put d equal to 0. Okay, let us try to understand this from the above figure, as you can see, which I have edited. So this is the incoming particle represented by a exponential I k1x. Okay, it is moving from left to right. Now it is striking the step or the barrier having height v0, right, at the position x equal to 0. Now some part will be reflected back, which is given by b exponential minus I k1x. So total will be your wave function psi 1 in region 1. Now some part will be transmitted, which is represented in region 2 by c exponential I k2x, and it is traveling again from left to right. But the problem is to have d exponential minus I k2x. Okay, so for this, which should be traveling from right to left, we should have another barrier at this position, which is not possible. So that is why this term d exponential of minus I k2x is not possible. That is why we have taken the constant d to be equal to 0, right? Okay, coming back, now let us apply the boundary condition. Okay, remember before that, taking d equal to 0, the wave functions in region 1 will be as it is, but in region 2 this will be only c exponential I k2x. Okay, only wave traveling from left to right. Now let us apply the boundary condition by using the continuity of the wave function psi and its first order derivative, that is d psi by dx at x equal to 0, so that psi 1 should be equal to psi 2 and d psi 1 by dx should be equal to d psi 2 by dx. Okay, so let us apply these boundary condition, and applying these on equation 9 and 10, we will find that A plus B equal to C from the first condition, and from the second condition I k1 into A minus B equal to I k2 C. And on solving, okay, you have to solve this. On solving, you can find the value of B coming out to be k1 minus k2 by k1 plus k2 into A, and C to be equal to 2k1 by k1 plus k2 into A. And here B and C represent the amplitude of reflected and transmitted waves respectively in terms of amplitude of incident wave, which is capital A, right? Now the coefficients of reflection and transmission can be defined as the ratio like this: the coefficient of reflection, which is capital R, it is equal to magnitude of reflected current divided by magnitude of incident current. Similarly, the coefficient of transmission, capital T, is equal to magnitude of transmitted current divided by magnitude of incident current. Now we will discuss two cases. First case, when the energy of the particle is greater than the barrier height, that is E greater than V0, and the second case when E is less than V0. So case 1, when E is greater than V0. So in this case, the term K2, which is the square root of 2m by h cross square E minus V0. So this E minus V0 should be positive, hence this K2 should be a real quantity. Okay, so in this case the current density capital J, okay, vector J will be equal to the real part of psi star h cross by Im d psi by dx x cape. Okay, so if Ji, Jr and Jt represents the magnitude of current density associated with the incident wave, reflected wave and transmitted wave respectively. Okay, I for incident, R for reflected, T for transmitted. Then we have Ji to be equal to the real part of, this is the incident wave, its complex conjugate it taken, then h cross by Im into d by dx of the incident wave. So if we solve it, finally we will get Ji to be equal to h cross k1 by m into mod a square. Okay, similarly for psi to be equal to b exponential minus I k1x, this is the reflected one, and c exponential minus I k2x, this is the transmitted one. We can find Jr to be equal to h cross k1 by m mod b square, and Jt to be equal to h cross k2 by m mod c square. Okay, so we can calculate now capital R and capital T. So the reflection and transmission coefficients will be capital R equal to Jr by Ji, so mod b square by mod a square. And if we put the value of b in this case by using equation which we have derived by using equation 13 and 14, okay, for the value of b and c, we will find R equal to k1 minus k2 square by k1 plus k2 square. Okay, similarly T, which is the ratio Jt by Ji, which will be mod c square by mod a square into k2 by k1, so that it will be 4k1 k2 by k1 plus k2 square. Again we have used the value of c from equation 14. So we can see that if we add R and T, then its value will be equal to 1. So this means that the total probability is always equal to unity, and the expression 19 and 20 for the reflection and transmission coefficients are similar to the laws of reflection and transmission of light between two media having different refractive indices. Now in case of particle waves, the expressions physically mean that a quantum particle will be partially reflected even if it has enough energy to propagate past the step potential, which is having a height v0, right? So this condition explains the nano physical behavior of the quantum world. which is quite different from the classical concept, right? Now from equation 19, clearly the reflection coefficient R will approach to 0 as K2 will approach to K1, that is if the barrier height V0 becomes equal to 0. Okay, and the value of R will approach to 1 as K2 approaches to 0, that is when E equal to V0, right? Thus the reflection coefficient will be 0 only if the barrier height is 0. Therefore there must be some reflection even if the energy is greater than your barrier height V0 as discussed in the beginning. Okay, so this was case 1. Now let us discuss the case 2 when the energy is less than the barrier height, so that E is less than V0. So in this case the value of K2 will be imaginary, right? Because this part E minus V0 will be negative because E is less than V0. So let us say that K2 equal to I, where I is the square root of minus 1. Okay, I into 2m by h cross square into V0 minus E to the power 1 by 2. Okay, and let us write this as K2 equal to I K dash, which is a imaginary value, right? And K dash equal to this much, which is a real quantity. Now K2 star, the complex conjugate, will be minus I K dash or minus K2, right? Now in region 2, that is with x greater than 0, we now have solutions c exponential minus k dash x and d exponential k dash x. Now here d exponential k dash x will have to be rejected again because it increases indefinitely, because as you can see in this part we have exponential to the power some positive quantity. Okay, so as x is greater than 0, so as x tends to infinity, it will increase indefinitely, okay, with respect to x. So this means it does not remain finite, which it should be for its physical acceptance, right? So in this case we have the wave function psi2 equal to c exponential minus k dash x, which is equal to c exponential I k2x, and psi 1 remain as it is, a exponential I k1x plus b exponential minus I k1x. Now let us apply the continuity of the wave function and its first order derivative at x equal to 0, which will give a plus b equal to c and I k1 a minus b equal to minus k dash c. Now we can solve these two equations and can have the value of b to be equal to k1 minus I k dash by k1 plus I k dash into a. Now if we substitute 10 alpha equal to k dash by k1, then we can have b equal to 1 minus I 10 alpha by 1 plus I 10 alpha into a, which can also be written as exponential of minus I alpha by exponential of I alpha into a, or simply b equal to exponential of minus 2I alpha into a. So you can see from this equation 24 that the magnitude is same. Okay, so here it is written that equation 24, that is the value of b that we have got in terms of a, tells us that there is a phase change or phase difference upon reflection, but the amplitude of the reflected wave will be same because they will have the same magnitude. Okay, so the reflected wave will be having the same amplitude as that of the incident wave. Now we can calculate the transmitted current, which is Jt, which will be the real part of psi 2 star then h cross by Im into d psi 2 by dx. Okay, upon solving this one, we can have finally Jt to be equal to h cross k2 by m into mod c square then exponential of minus 2 k dash x. Okay, and here we have replaced I k2 to be equal to minus k dash. Okay, so you can see this Jt will vanish in the region x greater than 0 because it is having this exponential term. Okay, so because of this factor, as the value of x increases, this will decrease this exponential term because exponential to the power minus something into x is there, right? So we can have the reflectance or the reflection coefficient r equal to 1, which can be calculated. Okay, and the transmission coefficient t to be equal to 0. Okay, and it should be noted that although the transmission coefficient that we have got is equal to 0, but the wave function is not 0. This is very important. Okay, in region 2 we have the transmission coefficient 0, but the wave function not equal to 0. Hence this means that there is a finite probability of finding the particle in the classically forbidden region, that is x greater than 0, because as per classical point of view, in the region 2 having x greater than 0, there is no existence of particle, but as per quantum mechanics there is some finite probability of finding the particle, right? But however, for the particle to be present in this region 2, that is x greater than 0, the uncertainty in its position will be how much? Delta x, which is nearly 1 by k dash, and therefore the uncertainty in its momentum as per Heisenberg's uncertainty principle will be delta p, which should be greater than or equal to h cross by delta x, that is nearly equal to your h cross k dash or square root of 2m v0 minus e, right? And similarly the uncertainty in the kinetic energy will be delta p square by 2m, so that it will be nearly equal to v0 minus e, which should be sufficient to bring it to the classically allowed region. Okay, so to observe the particle in the region 2, that is x greater than 0, we must impart some kinetic energy to the particle so that its total energy should become greater than this v0, right? Now the fact that r is equal to 1, this we can also calculate by using equation 24, which we have got for the value of b, because r is equal to how much? Mod b square by mod a square. Okay, this we have also calculated in the case 1, so it should be simply 1. Okay, so this is the calculated value of r. Now if a beam of electrons is made to incident upon the potential step from left to right, then in this case, that is having energy less than v0, that is the height of the barrier, all of the electrons will be reflected back and none of them will be transmitted, right? Acha, this is what the picture of your case 1 and case 2. Okay, so we have seen that the probability is finite for the case of energy less than v0. Okay, the probability of finding the particle in the forbidden region having x greater than 0, that is positive x, can be done by integrating the wave function over x. Okay, and we can take the limit from 0 to infinity. Okay, so it will be having a finite value and directly proportional to mod c square. Okay, so this is an example of your nano-physical tunneling effect, that is a particle can be sometime found where its energy is negative, that is E is less than V0, right? And therefore, which was the classical forbidden region, you can find this particle quantum mechanically, right? So this is the case 1 where we have the energy E is greater than the barrier height V0, and this is the case 2 where the energy E is less than V0, right? So this is what the tunneling of the particle up to a finite distance. Okay, thereafter it will be reflected back. Okay, so therefore in actual practice, the wave which is penetrating a very small distance from the boundary into the region 2, as we have seen in the figure, so this is continuously reflected till all the incident light is turned back into your region 1. Okay, so all the incident light will be turned back to your region 1, and due to such continuous reflection, the amplitude of the wave which is penetrating into region 2 will fall off exponentially. Okay, this is what shown in the bottom figure. This is the exponential fall or exponential decay of the amplitude of the wave. Okay, अच्छा तापरे जदि आमे देखिबा क्लासिकली the particle which is having energy less than the barrier height, that is E less than V0, can never penetrate into region 2 because its kinetic energy will be negative. Now on the other hand, in the nano-physical world, there is a finite probability of penetration of the particle wave through a very short distance into the classical forbidden region, that is region 2, having x greater than 0, and it will decay exponentially. Okay, this is the case of E less than V0. Now in case of E greater than V0, okay, we have found that mod C was greater than mod A since K1 was greater than K2. Hence, the amplitude of the transmitted wave will be more than the amplitude of the incident wave. Okay, this is what shown in the figure, the first one. So you can see this is the amplitude of the incident wave, but however the transmitted wave is having a greater amplitude. Okay, so in this case, the kinetic energy of the particle will be more in region 1, and hence its de Broglie wavelength will be less in region 1 with respect to that of in region 2. Okay, on the other hand, for the case of energy less than barrier height, that is E less than V0, the transmitted wave will be exponentially decaying with a very short distance, as we have seen in the region 2. Okay, so this is all about the application of Schrodinger equation to the case of potential step.
Thank you.